So I think we can start our session. So can anyone let me know whether I'm audible? Yeah, thank you. So let me just share my screen. So is my presentation visible? Yeah. So let's start our session for today. So good evening everyone. Welcome to week 4 live interaction session for the course Waste to Energy Conversion. Today's discussion will be on the topic of densification and the efficiency improvement in power plant. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself, Pratyumnan, a PhD scholar at the Department of Chemical Engineering, IIT Guwahati, is responsible for conducting a live interaction session every week. So, previously in the last three sessions, we discussed on the thermal conversion route. So, week 3 discussion closed with closed with all the three conversion routes where we discussed about each and every conversion route in detail. So can anyone name the three thermochemical conversion routes that we have discussed in the last three lectures? In just a quick recap. Yes. Yes. So these are the three processes. We have discussed each process in detail where we have seen their basics, the mechanism, their advantage, disadvantage, their application, the different types of reactors that are used for these process, and we have also solved, I would say, quite a good number of numericals on all the three concepts. And of course, we have also discussed about what separates each one of them. Even though they come under the branch of thermochemical conversion route, how each process is different from one another. So that is very important to remember. So I hope everybody is again able to recollect the basis of the difference between the three process lies in uh, the oxygen to fuel ratio. So how much amount of oxygen is used in each process distinguishes the three chemical thermochemical conversion routes. So one of the major problems, or you can say that one of the requirements for all the three thermochemical conversion route is that their feedstock, the raw material that you are going to feed in, which is in our case is a waste material, need to have uniform properties. So if you see the tabular column on for I guess in the last week where we have discussed about what is the typical raw material or what are the properties of the raw material that is required for each of the particular process. So one of the important requirement was that the feedstock should be uniform in nature, and which means that they should have uniform properties, physical as well as chemical. Their particle size should be uniform, so much. So for making this feedstock or the raw material to be uniform in nature, we do certain kind of pre-treatment process. So from there only this concept of densification starts. So densification is a method wherein we will try to make the waste material or the raw material of our interest uniform in nature so that they have uniform particle size. So now the question arises about why should the feedstock need to have uniform properties? What happens if my material or the waste material that I am taking has properties varying throughout the sample? So why do I require the feedstock properties to be uniform in nature? Any guesses? Okay, so uniform combustion, so that's fine. So because of uniform combustion, reduced. Okay. Yeah, that's all are the advantages of densification. So in general, to be very in general, we can say that we need to make sure that the feedstock have uniform property so that the combustion is uniform, so that the energy efficiency, the process efficiency is far more better. So at the end, we want that to be achieved. So whatever I am doing, I want to make sure that my process is more efficient. So this is not just in this concept or in any of the branches of science. This is true in life activities as well. We want to do, or we want to be best as possible. So the efficiency of the particular process needs to be enhanced. So that is one of the reason why we need to have uniform properties, and one of the ways to achieve this uniform property is through densification of solids or densification process. So this densification process is nothing but it is a kind of a process wherein you will try to increase the density of the material. So by increasing the density of the sample, or increasing the density of the waste material, we try to get better uniformity in properties. So upon improving our density, we try to achieve uniform properties with the almost similar or uniform particle size throughout the sample that we are taking for our waste to energy conversion process. So as such, somebody just now told that densification of the solids has multiple advantages. So can you list that advantages once again? Yes. Yeah, just wait a second. Let me list it down. Uniform combustion. Next, reduced dust production. So reduce smoke and dust production. Reduce the cost of transportation. Yes. Reduce the possibility of combustion during storage. So these are the advantages of densification process. So by making our feedstock uniform, or making the particles in the feedstock of uniform size, we will be able to achieve uniform combustion. So because of uniform combustion, our efficiency of the process is enhanced. Then reduce the smoke and dust production. So in case of the pyrolysis process, as you see, the amount of smoke that gets generated within the system will be too much. So we need to reduce that, because if so much smoke or dust gets produced, we need to again pre-treat the dust before sending it, outside in the atmosphere. So that again requires, additional equipments and the machineries, because you cannot just leave the smoke particles or the particulate matter in the dust or the smoke just like that in the atmosphere. So there are government rules and regulations wherein they specify that the particulate size in the smoke should be less than certain limits before it is released into the atmosphere. So such things needs to be processed before it is let out in the atmosphere. So that might require additional machineries, imposing a cost. So we need to come up with a certain techniques wherein the amount of dust or the smokes that gets produced by this pyrolysis process gets reduced, is decreased. So through densification we will be able to reduce smoke and dust production. Therefore we can make sure that the process is more environmental friendly. Reduce the cost of transportation. So since the material becomes more dense, so as such, as I said, densification means that you improve upon the properties, make the properties of the material uniform by increasing the density. So by increasing the density of the material, the energy density of the feedstock also, or of the waste material, also increases. So since energy density is nothing but how much amount of energy can the material hold in a unit volume. So since that gets increased, the amount of sample or the amount of waste material that is required for the transportation or that is required for the energy conversion decreases. So since that decreases, the amount of material that needs to sorry, let me just come back again. Since the energy density increases, so a lesser amount of material is required for the energy conversion process. Since less amount of the material is required for the energy conversion, lesser amount of the material is going to be transported for this process. So lesser the amount of material, reduce the cost of transportation. And then the final one is reduce the possibility of spontaneous combustion during storage. So these are the uh, advantages of the densification process. So now after this we actually move on to something so called as briquettes. So these briquettes are nothing but they are actually kind of a processed form of this waste material, wherein they are converted in a particular shape and size, so that the briquettes are usually uniform in size, uniform in particle size, so that their combustion is more efficient. So how does this densification process happens? There are four stages, right? Yes. Yes. Concretion and concentration. So is this right? Compaction, compression, concretion, and concentration of solids. So these are the four stages in which your waste material is going to be densified. So the first stage is the compaction. So what do you do in compaction? You just take the raw material or the feedstock or the waste material, and then you just apply pressure. So again, as I said, this also can come under the production of briquettes. Briquettes. So first process is compaction, wherein you apply pressure. So how much pressure do you apply in this compaction process? I mean, as such, this compaction process itself is broken down to three different processes based on the amount of pressure that you apply. So one is the high pressure, after that is intermediate pressure, and then the final one is low pressure. Am I right? Yes. So these are the three processes. I hope I am right. If you have any this thing, if you have anything to tell, then you can let me know. So basically in this compaction process, what we do is, so you have two particles, you apply pressure so that the distance between the two particles gets reduced. After this happens, what happens is, since the distance between the particles get reduced, these particles are interlocked with each other. So what happens is, in case of that, in case of the high pressure, so since you are going to put a pressure that is something greater than 500 megapascal, so what happens is, depending upon the composition of the material, that material, since it is subjected to high pressure, it will start secreting out, or it will start giving out the lignin. So this lignin will tend to bind the particles together. So upon high pressure, upon subjecting to high pressure, depending upon the composition of the material, because some material might have less lignin, some material might have more. So that depends upon the waste material that we are taking under consideration. The composition of the waste material, lignin is generated, lignin is generated, which sort of, like, you can say, glues or interlocks the particles in the system. So this is in case of the high pressure. So what about in case of the intermediate pressure or low pressure? Or let's first talk about low pressure before we move on to intermediate pressure. So here, upon applying the pressure, since the pressure is too much, the material sort of, like, generates, or basically the lignin gets out, and that lignin interlocks the particles in the system. But if you apply low pressure, the chances of this lignin getting generated will be very less. So in that case, what you will do, or in that case, what are we supposed to do? We can add binder. So binder is, yeah, so binder is like some sort of an adhesive which tends to interlock the system, or I'll write it better as, which binds the particles. So this binder is basically, what do you say, depending upon the pressure only, we need to really look whether a binder is required or not. So that is what is comes in the case of this intermediate pressure. So when you have this intermediate pressure, you may have binder, you may have to use binder, or you may not. So that depends upon how much amount of the pressure you're going to apply on the system, whether that much pressure is enough for it to interlock by itself, or does it require any sort of an additional or external binder to be applied in case of the low pressure system. But in case of the low pressure, it becomes compulsory that we need to use binder. So these binders are of, again, two different types. So this is based on their composition, or they yeah, this is based on their composition. So one is organic binders, and other one is inorganic binders. So any examples for organic binders and inorganic binders? Just one or two in each. Starch resin, okay. Even you can use, I guess, molasses also. So, and what about inorganic binders? Okay, clay and cement. So these are inorganic binders. Again, the type of binders that you use depends upon what kind of system you are having under consideration, or what kind of a waste material that you are going to use in your system for this energy generation process. So based on that, this will vary. Again, based on that, your pressure also will vary, what kind of the pressure you are going to apply onto your system. So So these binders basically have two kind of forces within them. One is your adhesive force and the other one is the cohesive force. This cohesive force are nothing but the forces between the two solid particles. So cohesive forces usually act between two similar nature materials, and adhesive force basically tend to bind at the solid and liquid interfaces. That is the two systems which are of different, which have different properties, are or you can say they are different in nature. So they bind usually through these two mechanisms. One is the adhesive and then the other one is the cohesive properties. So this densification process, again as we said, it happens through compaction. Then after compaction we have compression, then concretion, and then we have the concentration of the solid. So for this high pressure systems, we have four different types of press. So there are four different types of ways to press the feedstock material at such high pressure. So I will name two. I am expecting responses for the other three. One is the piston press, another one is the screw press, then next two, yes, pellet mill, pellet machines or pellet mills, anything is fine. So this piston press and screw press are something that is used in, in case when the amount of briquettes that you want to generate, or when the amount of material, waste material that you want to compact or compress is, when you want to compact is less. So these piston press and screw press are typically something that can be used in case of a low capacity system, whereas if you have roller press or your pellet machines, those are useful only in case of high capacity systems. So wherein you will tend to generate larger amount of briquettes. So this piston press, it's a very simple mechanism. So you need to feed your waste material, and then you will have a piston. So this piston will press the feed material. Again, the way the piston is going to press your material depends. There are two different ways. So you can check the lecture. There are two different ways, wherein one is through hydraulic pressure will be applied on the piston, and then another one I'm not sure. So there are two different ways in which your piston will press the waste material, and then because of this pressure the feed material will be compressed and form dense briquettes. So it's just that you have feed material, and then through piston, like how you see in syringe, so the movable portion is the piston. So there you apply the pressure, and then the feed material gets compacted and compressed, and it forms into dense briquettes. So one of the advantages of the piston press is the briquettes that are generated through this method are of high density. So typically the density range is either 2.5 grams per cc, or you can say 2500 kg per meter cube. So this is the density of the piston press. So sorry, density of the briquettes generated through the piston press method. This density is far more greater compared to the rest three. So in case of the screw press, roller press, or the pellet press, usually the density will vary between 1100 to 1400 or something lesser than that. So piston press is the only one that generates such high what do you say, density briquettes. In case of screw press, what happens is, it's something like, it works similar, very, it's as same as that of a screw extruder. So you will have the material. I hope you guys have can you know remember the schematic for the screw press. So, or I can say that, yeah. So in case of the screw press, what happens is you will feed the material into a barrel, and then that material will come down. It will then go towards the screw. It will then fall towards the screw. The screw is actually rotating in nature. So because of the rotating motion of the screw, the material that is fed through the barrel will also move. And because of this rotating motion, there is also a pressure gradient that is generated across this screw. So as the material moves and then the pressure gradient is developed, at the end, this due to this high pressure gradient, the material gets compacted and pressed and is then extruded out of the die in the form of briquettes. So this is about the screw press method. And in case of the screw press method, the quality of the briquettes that are generated are really very high in quality, high quality. So here it's just about, so in both these cases, in all these cases, in fact, you're going to apply pressure to your feed material so that you can get dense briquette. The way you're going to apply the pressure only distinguishes between the three, between all these type of machines that you see. So after this, we have something on, just a second. So these are the proper ways to generate the briquettes using high pressure. So in these cases, you apply the pressure and then the briquettes are generated. After this, we are actually going to burn the briquettes. Again, the reason why we want to make the briquettes is so that we can use the briquettes for the combustion process, so that the process is going to be more efficient. But again, this briquettes also has some more disadvantage. Even though it makes the process more efficient, but it also has certain disadvantages. One thing is the heating value in case of this briquettes needs to be improved. It is not of that high quality, or it's not of that these briquettes are going to have a very high heating value. Second thing is it cannot be stored under moisture condition. So any ideas on why these briquettes, which are pressurized through these systems, cannot be stored under this moist condition? What is the reason that the briquette cannot be stored under such a high moisture condition? So there are totally three advantages of the briquettes that gets produced through this method. Let me write that. Oh, we don't have space in this slide. Any ideas or any guesses on why moist condition is not suitable for these briquettes? Briquettes produce. You nothing to specify like that they are porous. I'm asking in general. Hmm. So that is fine, but what will the moisture do to the briquettes? If it absorbs moisture, so first briquettes produced through this method, heating value needs to be improved. And another thing is, even this briquettes, even though it gets densified, it does have generates quite a lot of smoke. Hmm. And more CO2 also. And then the third thing is moist conditions are not suitable. Yes, if the briquettes are porous in nature, if they have lot of void spaces within them, then they will absorb moisture. But what will that moisture do to those briquettes? Apart from reducing the heating value in the system. So, yes, moist condition, if it is present, then the briquette's heating value will further go low because it has water molecules, right? So, that kind of does not, allow it to properly, combust. But apart from that, what will happen to the briquettes if too much amount of moisture gets absorbed within the briquettes? So, what happens is we have talked about the concept of binder, right? So irrespective of whether it's a low pressure system, intermediate pressure system, or a high pressure system, for the interlocking between the particles you require some sort of a binder. Whether that binder gets generated inherently or externally we add as a matter of different is a completely different story. So we need to check that the binder should not be soluble in water, or you can say it should not be soluble in water. So what happens is if this binder is soluble in water, then the binder will it will start to get what do you say dissolve within water. It will just start getting removed between the particles which are keeping it intact. So once that binder is removed, these two particles will not remain in contact with each other. They will start fragmenting. Starts fragmenting. So the briquettes will be fragmented pieces. It will not remain in its compact form. So once that fragmentation happens and it turns into pieces, then automatically all the other properties that we discussed or all the other advantages of the briquettes that we discussed will be lost. Energy density will go low, and etc and etc and etc. So this is one of the reason why moist condition is not suitable for the briquette, because apart from the case of that it will reduce the heating value. If the binder that you're using within the system is soluble in water, then that binder will dissolve. So because of that the particles will lose the contact, because the binder only holds this particle together, interlocks them. So that will be lost and the briquettes will start fragmenting. So this is one of the reason why moist conditions are not suitable for briquettes. So any questions on this? Why briquettes are not suitable? I hope I have made it clear, but if you have doubts, then please let me know. Yes, any questions? I hope everybody gets what do you say an understanding on why moist condition is not suitable for briquettes. Again, this information is mentioned in the lecture, so if you go through the lecture very carefully, you will be able to find get this information. So again, moving on. So this briquettes, as we have discussed, it is if it is moist conditions are present, it is not suitable. It generates a lot of smoke, CO2 content is more, and heat. heating value needs to be improved. So how can you do this? How can you reduce the smoke and at the same time increase the heating value? By carbonization process. So if I ask a question, how to improve briquettes fuel quality, or let's say less CO2 smoke and more heating value, then the answer to this question is, as somebody rightly said, it is through carbonization. So through carbonization process, we will be able to make sure that the fuel quality that we are going to produce, or the briquettes quality, will be enhanced. So in order to do this process, we have two different types of reactors. So these reactors, one is uh, the rotary kin, or the stationary vessel with the sharing device, or another one is the shaft furnace. To do this, we use reactors. We use carbonization reactors, or yeah, that is correct, carbonization reactors. So we have two. One is your shaft furnace, and then the other one is your rotary kin, or you can say it is stationary vessel with sharing device. So this shaft furnace is used in case of, if the particle is porous in nature. Porous in nature with a medium particle size. Particle size. In case of the rotary kin, it is fine particles are used. So now the question is, so I hope you would have went through how the shaft furnace and the rotary kin works. So the question is, why can't I use this fine particles in the shaft furnace? Why is that the shaft furnace needs to use only this particles, only the particles which are porous in nature, or which have the medium particle size? What happens if, let's say, I don't have the idea on this carbonization reactors and I use fine particle in the shaft furnace? Question is, why can't I use fine particles in shaft furnace? Just a second. Any ideas on this? So if you see the course, the shaft furnace will have something like three columns. So in that columns, the particle, so the gas will be generated, and that columns will only transport this pyrolyzed gas. Actually, once the material is feeded into the combustion chamber, and then the pyrolysis process takes place, in the limited supply of oxygen, the pyrolysis gas will be generated. So this pyrolysis gas will go from this, or will, travel through the three columns, and then it will be taken into a combustion chamber. So think from that perspective of what will happen if I am going to use fine particles. think from the perspective of density, so you will be able to get. So the answer is quite simple. So fine particles are less dense, right? So when you're going to feed in the fine particles, already the pyrolyzed gas that is going to travel up. If you see, then in that case, what happens is the pyrolyzed gases will be traveling up, and then you will be feeding in this fine particles. So because of that, what happens is this fine particles, instead of going to the chamber where this pyrolysis process will take place, it will mix with this pyrolyzed gas that is already generated, and it will be taken away from the pyrolysis chamber. So because of that, that pyrolysis process efficiency, or the amount of material that is going to get carbonized or pyrolyzed, will decrease. So that is one of the reasons why fine particles should not be used in case of the shaft furnace. So less dense pyrolyzed gas will take away the particles along with them, resulting in decrease. So the the pyrolyzed gas will take away the particles, which will basically reduce the amount of fine particles entering inside the pyrolysis chamber, or you can say, yeah, the pyrolysis chamber. So because of that, the carbonized product that you're going to get outside of the system will be less. So this is one of the reason why fine particles should not be used in case of the shaft furnace. So apart from that, we have some discussion on the properties of the briquettes also, but we will discuss that along with some of the questions that we have. Before moving on to the questions or to the concept of properties of the briquettes, let's shift our focus towards improving the efficiency of the power plant. So again, as I said, um, we need to make sure that the power plant that we are using, or let's say the amount of the power that gets generated through this power plant, is more. So we need to feed it, we need to extract so much amount of energy, or we need to extract almost all of the time energy. Our goal should be to maximize the energy output from the raw material that we are going to feed in. So that is one of the major process, or you can say there is also much amount of the research going on in this direction, where you tend to develop reactors or develop system or develop process, make modification in the process in such a way that we can extract more amount of energy from what we are having it today, and from less quantity of the raw material, or with the given quantity of the raw material, what can I do, or what process modifications can be done, or what in general, what can be redesigned in such a way that the energy efficiency of the process is enhanced. Because this energy efficiency process, talking from the industrial perspective, it also directly is converted in the amount of money that is utilized in the process. So the energy efficiency directly relates to the profit that the industry makes. So even a small improvement in the efficiency of the process will help the, what do you say, the industry conserve, as well as uh, conserve, what do you say, will help in conserving most of the money that is utilized in process, and it will help in enhancing their profit. So this, even though it might look simple, it is not as simple as that. And still there are, and still almost every industry, whenever you ask them for a process to be so I'll put it this way. So all the industries usually ask, as engineers, to redesign the process or come up with a better design in such a way that the efficiency of the process to should be enhanced. So this is one of the reason why efficiency of the process should be, why we learn about improving the efficiency of the process. So in this case, if you see, we do not have much to discuss except for the fact that we have this Rankine cycle. So for the energy generation purpose, we use two types of turbine. One is a steam turbine and the other one is a gas turbine. So mainly in case of the steam turbine, we use this Rankine cycle. So this is the chart, or you can say, let me expand. So this is the temperature versus entropy diagram for the Rankine cycle. So these are the four different processes in case of a Rankine cycle. You have adiabatic compression, isobaric expansion, adiabatic expansion, and isobaric compression. So what happens is, you tend to uh, you know you tend to pump the liquid into your system through this reversible adiabatic compression process, after which the liquid is then sent to the boiler. In case of the boiler, what happens is the temperature is enhanced. So that, if you see here in this curve, this is between 2 to 3 where the isobaric expansion takes place. So isobaric expansion, as I mean, it happens at a constant pressure, isobaric constant pressure process. So over here, the temperature of your liquid is going to be enhanced. The liquid gets heated up, the temperature increases, and the liquid reaches its boiling point. After that, after a certain period of time, once you keep what do you say, boiling, the steam will get generated, and that's what you can see here. So this is about the isobaric expansion. So the liquid is converted into steam in the boiler. This steam is then, what do you say, fed into your turbine. So this steam moves into the turbine and expands adiabatically. So adiabatically expansion in the sense, there is no heat, what do you say, released, or there is no heat that is going to be released to the surrounding. The heat will remain conserved. After it expands adiabatically, the condense, so it will condense, right? So that condensed liquid is then compressed at a constant pressure, or the, I would say, sorry, so the condensed vapor is then compressed into the liquid through isobaric process. So this is for the Rankine cycle, and then the efficiency of the Rankine cycle is given as the work done by the turbine. So the turbine will rotate, and because of the rotation of the turbine, that rotation of the turbine is converted to power. So so the efficiency will be given as the work done by the turbine, so the rotation of the turbine, to the amount of heat energy that is fed into the system. So if you see here, this the line, that is the 3 4s. So this should happen in case if the Rankine cycle is an ideal Rankine cycle. But since no process is happens in an ideal condition, so that's the reason you have a, what do you say, kind of a slanting line from 3 to 4. So this is for the steam turbine. In case if it is a gas turbine, if you're not going to use a liquid, in uh, other than liquid, if you're going to use air, then you have this Brayton cycle. So this is an ideal Brayton cycle. So the first 1 2 process is Again, this one will be isoentropic, and then 2 to 3 over there, what happens is the system gets heated up, so at constant pressure. So this is isobaric. Then again, this Brayton cycle, Rankine cycle, the process is almost similar, except for the case that in case of the steam turbine, you use steam, or you use the liquid which is then converted to steam. Here you use air. That air gets pressurized and compressed, and then that compressed as well as that of the that pressurized and the heated air goes to the gas turbine and rotates the gas turbine, which is then converted in the form of power. The Once the gas loses its pressure as well as that of the heat, it then comes back to its original condition. So this is in case of the Rankine cycle and the Brayton cycle. So this is the formula for calculating the efficiency of the process, which is nothing but 1 minus T1 by T2, or you can also write it in terms of pressure as 1 minus P1 by P2, 1 minus gamma by gamma, where gamma is the specific heat ratio, which is nothing but Cp by Cv. So Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. So this is about the Rankine cycle and Brayton cycle. So let's move to our problem solving session, or the so till now we have actually had a recap on what we have learned. So today we had a lot of discussion because there were a lot of what do you say, theory to cover. So let's start with the problem solving session now. Before that, if you have any doubts, then please let me know. Yes, any doubts? So meanwhile, the question one, I hope if, you'll be able to tell the answer. Which of the following statement is not true about densification? But do you have any doubts with respect to what we have discussed before that? So we have answered. But apart from that, any doubts? I mean, whatever we have discussed till now, Rankine cycle, Brayton cycle. Okay, so first question. Somebody has told the option as, I guess. So its answer option is D. The dust production actually in case of densification is reduced, but it is given here that it increases dust production. So that is something that is not true for the densification of the solid. So second question is, friability index of 0 indicates what? So concept of friability is nothing but, if you take the briquettes, if you try to, what do you say, kind of sieve those briquettes, the amount of material that gets retained is called friability. The amount of material retained in a 200 in a sorry in a 20 sieve. So this is nothing, this is called as the index of friability. So friability is nothing but it's the resistance to mechanical shock. So once you give some sort of a mechanical shock to the material will tend to break. So you take the broken briquettes. So here, since we are discussing about the briquettes, you have briquette, you give a mechanical shock, it will tend to break. You take that broken briquettes, whatever that briquettes that gets generated after subjecting to the thermal shock, after sorry, subjecting to the mechanical shock, you take that briquettes and you try to, what do you say, sieve them in a 20 mm sieve. The amount of material that gets generated or that gets retained within the 20 mm sieve is called index of friability, and then subjecting the briquette to this mechanical shock is called this process is called friability. Subjecting briquettes to, yeah, mechanical shock. So index of friability is amount of material retained in a 20 mm sieve. So friability index is 0, which means no material is going to be retained in a 20 mm sieve. So what could be the option? It has good quality, inadequate quality, both A and B, or none of this. I guess somebody has answered B. Okay. So somebody says that the quality will be inadequate. So why do you, I mean, what is the basis behind this, or what, like, what do you say? What is the thought process behind this in saying that if the friability index is going to be 0, then the quality of it is going to be inadequate? I mean, what is the reasoning? Then if the mechanical strength is more, then nothing, I mean, everything should be retained, right? So if the mechanical strength is more, then if you subject to some sort of a mechanical shock as per the definition, then the briquette should not break. So if the briquettes does not break, then whatever amount of briquettes that you are going to put in the sieve will remain as such. So then in that case, briquette friability index will not be 0. It will be something else, some other value. So friability index of 0, let me explain that. So friability index of 0 means no material is going to be retained in that 20 mm sieve. All the material will pass through that sieve. So for the briquettes, what do you say? For the briquettes to have that uniform combustion, it needs to be strong. So that is the adequate quality of a briquette. That is the particular quality that we want the briquette to exhibit. So this is the reasoning. Since you are subjecting it to mechanical shock, and then none of the material is going to be retained in the 20 mm sieve. So which means that all the briquettes are fragmented, are broken. So, but we want a briquette which needs to have uniform property and to be strong, so that the heating value can be improved, energy density can be improved. But if all the material are going to be fragmented, then that particular briquette will not have good value. So it will be of inadequate quality briquette. Is it fine? Requirement is briquette should be good, irrespective of whether you subject to any sort of a mechanical shock or not. So briquette should be strong. That is the quality that we expect. But here what we are getting is, once we apply the shock, mechanical shock, or you can say instead of a shock, mechanical pressure, the briquettes are going to be broken in such a way that there is no material that is going to be retained in the sieve. This is exactly opposite of what we wanted. So the quality here is inadequate in nature. It is not a very good briquette to be used for this energy conversion process. Is the explanation okay, or any uh, misconception or anything that is confusing? Okay, somebody has told okay. What about others? So briquettes need are feedstock are compacted to form briquettes, so that they are uniform in property, they are strong, and then their, what do you say, combustion is more efficient. And this should be there in irrespective of any kind of a shock or whatever it is, you're subjecting those briquettes to. But here, when we subjected a particular briquette, it got fragmented, broken in such a way that if you put that broken pieces into a 20 sieve, all that broken briquettes pass through that sieve and nothing is retained. So this is something exactly opposite of what we want our briquettes to be. So we can say that the quality here is inadequate in nature, or it's not something that is, the quality is not good in general. So let me write this. So zero index means, so zero as an index means no material is retained in 20 C. We want our briquettes to be more dense, so that its property, specifically the combustion, is enhanced. However, as per our as per the question, all briquettes are fragmented, which is something undesirable quality of the briquette, which is something of undesirable quality. And that's how we say that the briquettes which we have is inadequate, or the briquettes that we have are inadequate in quality. So let's move to our next question. Question number 3. If you have any doubts, please let me know. Question number 3 is, based on compaction, the types of briquetting techniques are. This is a very easy one. We have discussed this. Yes, this is the most, I think, easiest question among all four. uh, I guess we have somebody else also responding. So D, okay. As such, we discussed previously high pressure compaction, uh, low pressure with binder, medium pressure with or without binder. That is something which is depends upon the type of the material that you use. So all of the above is the answer: high pressure, low pressure, and medium pressure. Now coming to question 4, the overall energy production from a waste treatment facility, or you can say, yeah, facility, depends upon heating value of the waste, efficiency of the thermal processing unit, efficiency of the turbine generator. D, okay. Any other response, or is the option correct? Somebody has told me the answer as option D. So the option is D. Uh, the more so the overall energy production depends upon all the three factors: heating value, efficiency of the thermal processing unit, and efficiency of the turbine generator that is used. So here we are taking the overall, like starting from the, what do you say, kind of the pyrolysis of the waste till the energy that gets generated as in the form of a power. All the things we are including, and then we are stating that the overall energy production depends upon all the systems. So this overall is the for the entire process of starting from the starting from, using the waste material to the energy generation, the ultimate, the final point of power generation. So it depends upon all the three. Now, let's move on towards our first question. So, any doubts on our discussion till now related to this densification of the solid, efficiency improvement, Rankine cycle, Brayton cycle, and then these four questions? So, based on this, let me put forward one question, which it is a very sort of like simple one. So we have discussed about that moist condition, right? So the, what do you say, the briquettes that you're going to use should, what do you say, kind of are not able to, you cannot store them under the moist condition because they tend to absorb the moisture. So are there any tests to identify how much amount of the moisture will this briquettes absorb? Is there any test so that we can determine the amount of moisture the briquettes can absorb. Because we have discussed why moist conditions are not suitable for storing, are not suitable for storing briquettes, because they tend to, if the binder is soluble, if the binder is soluble in the water, then it will get removed, and because of that the fragmentation will happen. But to determine whether the briquettes will be suitable for moisture condition or not, there are certain tests which can be done to identify. So there are totally two tests. So does anybody have any idea, or can they describe it here? And another one, immersion test. So immersion test is nothing but you take the briquette and then you drop it in water and then allow the briquettes to absorb the moisture, and if it does absorb water, then it will expand. So based on the amount of what do you say, the weight difference within the briquettes, you can easily get to know how much amount of the moisture is absorbed by the briquettes. There is another one test. So instead of water, you can also put it in moist air conditions. Like the standard condition that is used for these tests is, if you keep the briquettes at 20 degrees Celsius in a air which has 95 percentage moisture, or you can say 95 percentage humid, and if you keep that briquette for 21 days, then depending upon the elongation or the expansion of the briquette, you can determine the amount of moisture the briquettes absorb. So these are the two things that is related to determine how much amount of moisture the briquettes can absorb. So now let's move on to the question. Question number 5. It's a very simple question. In a municipal solid waste gasifier, air flow rate is given as 10 Newton meter cube per second and feed flow rate is 5 kg per second. It is stated that the municipal solid waste that we are going to take does not contain any sulfur, nitrogen or chloride in them. The syngas, whatever, I mean, once you do the gasification process, the syngas is going to be generated. This syngas contains CO, carbon monoxide 30 percentage, CO2 5 percentage, H2 35 percentage, CH4 methane 5 percentage, and C2H2 acetylene as 3 percentage. Calculate the rate of production of syngas in Newton meter cube per kg of the municipal solid waste. So we need to calculate the fuel production rate, sorry, syngas production rate. How to solve? I can keep it as syngas production rate. So formula, anybody remember the formula? Yes, formula anyone? We have an answer from. So it is, can I write it like this? Airflow rate times 0.79 by 1 minus the percentage of carbon monoxide plus carbon dioxide plus hydrogen gas plus methane plus C2H2 acetylene times feeding rate. Is this correct? I mean the formula. Yeah, so I have given the formula. Now I think you will be able to calculate. So let me also calculate side by. Airflow rate is 10 times 0.79 divided by 1 minus. So here I am taking everything in percentages as such converted. So I am not going to use that by 100. So carbon monoxide is zero point 0.3. Carbon dioxide is 0.05. Hydrogen gas is 0.35. Oh, sorry. Methane is 0.05 again. And acetylene is 0.03 times the feeding rate. So which will be nothing but 5 kg per second. So 5. Is this okay? So then syngas production rate would be 7.9 divided by 5 times 1 minus. So this will be 0.35, 0.35, 0.7, 0.7, 0.78. So this will be nothing but 7.9 by 5 times 1 minus 0.78 is 0.22. So this will be nothing but 7.9 by 1.1. Let's use the calculator. 7.1818. Let me get a 7.18 Newton meter cube per kg of MSW, municipal solid waste. Is this correct? Any other answers? Any other answers? Yes. Any other answers? Or have I done any mistake? My screen is visible, right? Okay, that's fine. Yes, any response? It's okay, like 7.18. Okay, okay. I hope others are also getting the same answers. If not, please let me know now before we progress for the next question. So let me just move on. Okay. Let's do this question. Or better, we will do this question first. Yes, that will be fine. So, a pine needle is used to produce bio oil in a slow pyrolysis unit. The percentage of bio oil, char, and gas are 30%, 40%, and 30%. Average molecular formula of biochar is given as CH.56, oxygen as 0.28, and nitrogen as 0.013. And for the bio oil, it is C H 1.47, oxygen as 0.36, and nitrogen as 0.005. Composition of the whatever the gas is going to be generated from the pyrolysis unit is: hydrogen gas is 10, carbon dioxide is 46, carbon monoxide is 30, and methane is 14 percentage. We are supposed to calculate the percentage of the carbon converted to bio oil. It's a very simple one, so please let me know how to solve. Uh, okay. Hmm. 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 Okay, of individual, both the biochar, bio oil, as well as the gas. And then mm, mm, mm. Moles of bio. Mm, 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 mm. So then we will calculate the total number of moles, and then yeah. So okay. So the process is correct. So yes. Okay. Yeah, but then the this is just for practice purpose. Yeah, that's the reason. So then for the others, try. So first you need to assume that the pine needle is of 100 grams, like the base, and then from there you can again that considering that base is up to you whether you want or you don't want, it's fine, but it's to make the process more easier. So consider the basis of pine needle as 100 grams, and then from there the bio oil will be 30 grams, char will be 40 grams, gas will be 30 grams. You have the average molecular weight. Multiplying that with their atomic masses will give you the average molecular weight of the system for each bio oil as well as biochar. Composition is given for hydrogen, composition is given for a gas. From that composition, you can calculate the average molecular weight of the gas also. Once you calculate the average molecular weight of biochar, bio oil as well as biogas or whatever that gas is generated, flue gas, what you can do is you can find out the number of moles, because you know the amount of oil, char as well as that of the gas present in your system. From there you can calculate the number of moles. Once you calculate the number of moles, you can find out the percentage of carbon in each. You can get to know the number of moles of carbon in bio oil, biochar as well as your gas. From there you can come to know what is the carbon present in the bio oil. So let's start solving this. It will take some time because it's you need to take up you need to calculate multiple average molecular weights. So 100 gram of pine needles is assumed. Again, if anybody has solved this question, I mean the same values, then please let me know the answer. So which means your bio oil will be 30 grams, char will be 40 grams, and your gas, whatever that gas is going to generate out of the pyrolysis unit, will be 30 grams again. So this is known. Now we have the molecular formula for yeah, whatever molecular formula for biochar as uh, uh, I think somebody's the can you mute? Excuse me, Mrs. Valsa Kumari, can you please mute your mic? Yeah, yeah, yeah. That's fine. So, molecular formula of biochar is CH.56, oxygen as 0.28, The nitrogen is 0.013, and molecular formula for bio oil is CH 1.47, oxygen as 0.36, and nitrogen as 0.005. So for this we need to calculate the average molecular weight. So here you take the coefficients and then multiply it with their atomic mass. So carbon is 1, so 1 times 12, plus hydrogen is 1, again atomic mass, so 0.56 times 1, plus oxygen is 0.28 times its atomic mass is 16, plus nitrogen is 0.13, sorry, 0.13 times 14. So this is the value. This is the way to calculate. So please let me know what is the average molecular weight that you're getting for biochar and bio oil. Let me just separate this. So let's calculate this. 0.28 times 16, 0.48. So it will be 12.56 plus 4.48 plus 0.013 times 14, 0.013 times 14, 0.182. So we need to add all this. So 0.182 plus 4.48 plus 12.58. 17.24. It will be 24. Yeah, 17.24. These many gram per mole. Similarly, again, it will be here 13.46, 16 times 0.36 is 5.76, 14 times 0.005, 0.07. So that will be 13.46 plus 0.07 plus 5.76, 19.29. So the reason why I am solving this is, even though it is simple, we tend to make mistakes while calculating the molecular weight also. So that is the reason why I am calculating the molecular weight also in the live session. So it is expected that you also solve parallelly with me, and then please let me know the answer if in case you get it before I finish solving the problem. So for the gas it would be 0.01 sorry, 0.1 times hydrogen gas is 2, 0.46 times carbon dioxide is 44, plus carbon monoxide is 0.30 times 28, 0.14 times 16. So let me calculate in my personal calculator this one, so that we can, it will be easy. 31.08 gram per mole. So this is the molecular weight or average molecular weight of biochar, bio-oil as well as the biogas. From here you need to calculate the number of moles of bio-oil, biochar and gas. So of bio-oil will be 30 by, what is the average molecular weight of bio-oil? 19.29. So that would be around 1.555. So I'll keep it as 1.55 moles. Okay. So number of moles of biochar will be, for biochar it is 40 grams. So 40 by 17.24. Sorry, this is my mistake. 40 point by 17.24. 2.32. And number of moles of gas will be, again, 30 by, it would be 31.08. So how much would that be? 30 by 31.08. 0.965 moles. 0.965 moles. So what would be the total number of moles? So since for every mole of bio oil you have 1 mole of carbon, so this will be same as the number of carbon atoms in number of carbon, you can say, what do you say, number of moles of carbon present in bio oil. Similarly this will be same as, see, present in biochar. This will be also same as number of moles of C present in gas. So number of moles of carbon moles will be nothing but 1.55 plus 2.32 plus 0.965. How much would that be? 1.55 plus 0.965 plus 2.32. 4.835 is the total number of moles. So you need to see what is the percentage of carbon only in bio oil. So that will be one, bio oil is 1.55, right? So 1.55 by 4.835. 0.32 or 32.05 percentage carbon present in, or you can say carbon converted to bio oil. So this is how you will calculate the percentage of the carbon converted to bio oil. Is my answer same as yours, or is there anything different? Because since it involves calculation of this average molecular weight, there are chances that there could have been calculation errors. Yes, anyone? Oh, sorry. So since we started actually at around 5:10, we will continue up till 7:10. So that's a like extra 10 more minutes. So this will be useful for your assignment. So you know that is one of the reason why we are conducting live interaction sessions, so that sometimes what happens is all those things, since every week we learn around 4 to 5 modules, we might miss out on, or we might forget many of the stuff. So that is the specific reason why it's on a Sunday, because you tend to have a recap of whatever you have learned throughout the week and solve some of the problems, so that it will help you in your assignment as well as the final exam that some of you might be taking. So let me progress to the next question. So we have around two questions for this particular week and two more which we haven't solved it for week 2 lecture, I believe. So let's see how much we can solve for today. Question number 8. This is very straightforward. So a 10-ton hydraulic jack is used to lift machine component and compress the briquettes. Compaction force can be calculated using the pressure. Pressure from the pressure gauge is measured to be 17.5 kilonewton per meter square. The machine has 50 moles and then the diameter of the briquette sample is 30 mm. Calculate the compaction pressure. It's a straightforward question. So, uh, so anything in the previous question, you can let me know, or please tell me how to solve the question number 8. So, I will ask one more question. How to calculate force from pressure? Compaction force. How to calculate, or how to use the pressure, compaction pressure that is given in the question to calculate the compaction force. What is the relationship between force and pressure? Hmm. Pressure is equal to force by area. Yeah. Or you can write it as compaction pressure is equal to compaction pressure times its area, right? Is it fine? So how do you calculate area now? It is area. So briquette, you are considering it as what do you say? As a cylinder with the diameter of 30 mm. So we have bothered only about the cross sectional area. So that would be nothing but pi by 4 d square. So we are only considering about the what do you say, that the diameter, the circular part of our briquette, which is actually going to create that pressure, which is going to, you can say subject to pressure. Is it fine? So you just need to calculate. This is for area of what you can say, for one mold. Like that, you're going to have 50. So total area will be 50 times the area of each one. So that would be 50 times 3.14 times 0.03 times 0.03 divided by 4 times 3.14 times 0.03, this by 4. 0.0353 meter square. So this is going to be the area of, the machine, the moles. Yes. So if you have, you can mute your mic if you have something that you would like to tell, what do you say? If you want to just, give some input related to the question, then you can unmute your mic. But it is better, I suggest everyone to unmute themselves so that, I can know whether they are asking some question to me or not. So compaction force will be 17.5 is the compaction pressure, but it is in kilonewton, so that times 1000 times 0.0353 meter square. So that will be 17.5 times 35.3, 617.75 Newton. Is the answer fine? I don't think there would be any. I mean, this is a very basic question. So it's just that the machine molds are there, and then they are going to, what do you say? They are just going to compact the briquette, and then the diameter of the briquette sample is given, and then, the compaction pressure is also given. So you just need to calculate the compaction force. Yes, others, any doubts? I mean, this is a very simple one. We have one more question. Again, that is also a straightforward question, so there's not much to discuss there. So let me show that question here before. Calculate the thermal efficiency of the power plant if the heat rate generated is 3233 or 3200 kilocalorie per kilowatt hour. It's just a straightforward question. Thermal efficiency needs to be calculated. This should be a very straightforward question. You can let me know the answer of what will be the. It is, I will just give the formula. I will calculate it and then, I'll post the answer when I'm uploading the presentation. But the formula is 100 times 859.845 by your heat rate. This will be in percentage. That's all. So it's a very simple question. So you will be able to solve. It's just that you need to substitute this 3233 in terms in the place of that heat rate. So, but before that, I will describe what is thermal efficiency. So, the thermal efficiency can be expressed as the electrical energy output to the amount of, what do you say, the heat supply. This will be the thermal efficiency. The heat rate will be exactly the inverse of this. It will be the heat supplied to the electrical energy output. Yes, somebody has 26.59. I hope that answer is right. Okay, since one of them have given us the answer, let's calculate. 85984.56 by 3233. 26.59 percentage. Is that the answer? Same, 26.59 percentage. So that is correct. So thermal efficiency is 26.59 percentage. So again, this is just based on the formula. If you're given with the mass and then specific heat, then you need to substitute them and then you need to calculate. Let's take one sort of a problem in the next class before we begin our discussion related to week 5, session related to week 5 course content. So till now, do you have any doubts related to what we have discussed today? Anything? Okay, no. So that's, let me stop presenting. Okay. So if you have any doubts, please let me know. I hope you're able to get all the presentations and you're able to access them. So in case if you're not able to access them, please go to the course content, like the page where you can actually go for every single week's course related videos. Over there in the left hand side at the bottom, you can see the problem solving session. If you click on that link, you will be directed to a Google spreadsheet where the recordings of this live interaction session as well as the presentations that we are using for this live interaction session will be uploaded. You can always look at them, and then if you have any doubts, then please do email to me. My email ID will be present there. So there is a query from Ritika stating that what type of questions are going to come in the exam. So as such, I do not have any particular idea on what kind of questions will be there, but you can definitely, I can definitely say, and you can definitely hope that the questions will be of same, nature as you do, in your assignments. There will be problems and there will be theories, like how you have it in your assignment. A similar pattern will, you can expect during your, what do you say, the final exam. But I would say that the right person to confirm this will be, the other TAs who are responsible for this course. So I would encourage you to post this question in the Q&A section of this particular course. So in the, top section, you can find a particular icon for the Q&A. If you click on that, you'll be directed to a Google Groups. So over there, you can post your questions. So they will be surely responding to that. So yeah, but something very similar to what you solve for your assignments. So apart from that, if you don't have any doubts, I think we can conclude our session for today. Okay, so do post your questions there. You will surely get answer to that. Yeah. So let me, yeah. So let me conclude the session for today. So thank you everybody for joining today's live interaction session. Our next live interaction session will be on 23rd February, same 5 p.m. to 7 p.m. So that so we have completed four. I mean, we have almost reached half of the course content is over. So let's meet on next Sunday, 5 p.m. to 7 p.m. Till then, bye, and do what solve your assignments. Bye. Thank you.